deep beneath the cosmic silence, something impossible is happening. In the heart of a galaxy 1.5 billion light-years away, astronomers observed a ripple wave through space-time itself. But this one was different, violent, off rhythm, as if the fabric of reality had snagged. What if, somewhere out there, a black hole didn't just pull things in but broke the rules entirely? What if the thing we thought was the endpoint of physics was just the beginning of something far stranger? Could we be witnessing a tear not just in space, but in the code that writes the universe itself? Join us as we dive into the deepest mystery of the cosmos, where black holes don't just consume matter, they might be rewriting reality. Subscribe if you believe the universe still has secrets to give. It began not with an explosion, but with a whisper. On a quiet morning in September 2015, a tiny ripple passed through Earth, imperceptible to every living creature, but not to the twin LIGO detectors in Washington and Louisiana. What they heard was a faint, chirping signal, a gravitational wave. After decades of theory and silence, Einstein's elusive prediction had finally spoken, but the world only heard half the story. Buried in the background noise of that momentous detection, like static behind a radio broadcast, was something else. A flicker, an inconsistency, a tremor in the data that didn't follow any known pattern. At first, the team at LIGO brushed it off as instrumental interference. Solar flares, seismic murmurs, hardware noise, there are dozens of things that can contaminate a signal. But one postdoc didn't let it go. Her name was Dr. Elena Ruiz, a young astrophysicist with a penchant for seeing patterns where others saw randomness. Late one night, poring over waveforms in LIGO's archive, she noticed the anomaly wasn't alone. There were faint echoes, tiny distortions in other gravitational wave detections, and all of them shared one eerie trait: a sharp, needle-like spike in the waveform, not a smooth chirp, a pierced dot, the kind of pattern that shouldn't exist in a smooth fabric of space. She called it the tear. Ruiz's findings were initially met with skepticism. She submitted the anomaly to her supervisor, who dismissed it as software aliasing. But behind closed doors, other scientists whispered, what if this was not a bug, but a message? What if the spike was not from within the black hole merger, but from what the merger was revealing? You see, black holes don't just bend space-time, they reshape it, and under certain extreme conditions, they may even do something else, something terrifying. They might break it. Let's pause here for a moment. Imagine the fabric of reality as a sheet stretched tight. Gravity, energy, time, everything moves across this surface. A black hole is like a weight, stretching the sheet downward. But what if, instead of just deforming it, the weight pierced it? And what happens when reality gets pierced? Dr. Ruiz wasn't alone in wondering. A handful of gravitational physicists across the globe began to notice the same strange data in different merger events. In Poland, in South Korea, in Australia, different detectors, different instruments, same impossible spike. A quiet sense of dread began to spread through the community, because these were not random errors. They were consistent, timed, spaced. Coordinated. Ruiz partnered with a data scientist from MIT named Jordan Malik, who applied deep learning techniques to LIGO's archives. The AI filtered out false positives and honed in on waveforms with similar anomalies. When the program finished, the result was jaw-dropping. 5 more spikes, all linked to Kerr-type black holes, a specific kind of rotating black hole, theorized to spin so fast it drags spacetime with it, and each one followed the same signature profile. Now, the question wasn't just what these spikes were. The question was, why do only rotating black holes tear spacetime? The implications were disturbing. Some physicists speculated that, at extreme rotational velocities, the spin could twist the spacetime fabric until it frayed like a drill boring through a wall. If that's true, then we are no longer dealing with gravity as we know it. We are witnessing a phenomenon that rips the playbook of physics wide open. But Dr. Ruiz took it a step further. In a now famous 2022 symposium, she raised a question that left the room silent. What if these aren't just tears, but doors? Doors to where? To what? No one answered. Because to even imagine that is to challenge the boundaries of science and the safety of reality as the LEGO team began preparing for their next generation upgrades. Rumors swirled in academic circles. Funding was being redirected. Data was being re-analyzed. And in observatories around the world, eyes were turning not to stars or planets, but to black holes, to the anomalies, to the spikes, to the whispers in the gravitational deep, because maybe, just maybe, the universe is trying to tell us something. But are we ready to listen? Before we can begin to understand whether black holes are tearing holes in spacetime, we must first understand what they are. To most, a black hole is a simple concept, a place in space where gravity is so strong that not even light can escape. But that definition barely scratches the surface. A black hole isn't just an object, it's a phenomenon, a wound in reality itself. A place where the known laws of physics fold inward, and the very geometry of the universe curves to an infinite point. We didn't always believe in them. In 1915, Albert Einstein published his general theory of relativity. With it, he rewrote gravity not as a force, but as a warping of spacetime itself. That same year, a little-known German physicist named Karl Schwarzschild solved Einstein's equations for a point Mersenne stumbled upon a terrifying mathematical singularity, a place where spacetime curvature becomes infinite. He described a radius beyond which nothing, not even light, could escape. It was later called the Schwarzschild radius. At first, the idea was seen as purely mathematical. No one believed something so extreme could exist in nature. But nature doesn't ask for our permission. Fast forward to 1967. Astronomer Jocelyn Bell Burnell discovers an unusually regular pulsing signal in the Skya pulsar. And then came Cygnus X1, a binary star system with a dark companion so massive and dense it could only be explained as a black hole. Suddenly, the mathematical ghost had a face. Black holes exist, and not just as rare freaks of physics but as common endpoints in the lives of massive stars. But here's where things get strange. The core of a black hole, the singularity, is not just dense, it's unknowable. It's where general relativity and quantum mechanics clash violently. Einstein's equations collapse at this point, and that's a problem. Because if our laws of physics break down, then we no longer understand the thing controlling vast regions of space, and black holes are everywhere. There are stellar mass black holes formed from collapsing stars, each just a few kilometers wide. But at the hearts of galaxies, including our own, lie supermassive black holes, millions or even billions of times the mass of our Sun. Sagittarius A*, the behemoth anchoring the Milky Way, is about 4 million solar masses, and we don't know how it got there. We also don't know what lies inside. For decades, physicists assumed the event horizon, the point of no return, was just that, a one-way membrane, Anything crossing it would fall inward forever, crushed to infinite density. But in the 1970s, a young physicist named Stephen Hawking changed everything. He theorized that black holes might slowly evaporate via quantum fluctuations near the event horizon, a phenomenon now called Hawking radiation. Suddenly, black holes weren't just eternal prisons. They could leak, they could die. But that led to an even more disturbing thought. If black holes evaporate, what happens to the information inside them? According to quantum theory, information can't be destroyed. But if black holes erase it, something fundamental breaks in our understanding of the universe. This is known as the black hole information paradox, and it still haunts physics to this day. To solve it, some theorists proposed radical ideas that information is stored on the event horizon like a cosmic hologram, or that black holes are gateways to baby universes. Others speculated about wormholes, or even multiversal recycling engines. The truth, we don't know, but what we do know is this: black holes are not just dead zones in space. They are engines of extreme physics. At their boundaries, time stretches, matter spirals at relativistic speeds, energies spike to unimaginable levels, and at their core, reality twists beyond recognition. That makes them the perfect suspects. If something were to rip spacetime, wouldn't it be the very object that already stretches it to its limit? This brings us back to the anomaly Dr. Ruiz observed. The tear wasn't a byproduct of a normal black hole. It appeared only during events involving spinning black holes, what physicists call Kerr black holes. These monsters aren't just gravitational wells. They twist spacetime itself as they rotate, dragging the fabric of the universe along with them. Imagine stirring a spoon in honey. The honey near the spoon starts to swirl. Now imagine the spoon is rotating at nearly the speed of light. What happens to the honey then? What happens to spacetime? That's what we'll explore in the next chapter, because Kerr black holes may not just warp the rules, they might rewrite them. Let's imagine you're falling toward a black hole. First, the stars above still shimmer, the cosmos stretching out like a canvas. But the closer you approach the event horizon, the more reality begins to bend. Light itself starts to curve inward, spiraling around a dark core. Time slows, space warps, and just before you cross that final, invisible line, the universe as you know it ceases to make sense. This is the event horizon, the point beyond which nothing escapes, not matter, not radiation, not even light. And yet, it may be hiding something even stranger than darkness. For decades, the event horizon has been treated as a cosmic one-way door. Cross it, and you're lost forever. A star that drifts too close is shredded into a stream of glowing matter. An astronaut falling in would be stretched spaghettified. Those gravity pulls harder on their feet than their head. These are the horrors of tidal forces in the black hole's grip. But now, physicists are asking, what if the event horizon isn't just a border, but a membrane? In classical general relativity, nothing remarkable is supposed to happen at the horizon. It's just the place where the escape velocity equals the speed of light. But quantum mechanics, mysterious and unstoppable, doesn't agree. New theories suggest something bizarre happens at this boundary. One such mystery is time. From the outside, an object falling into a black hole appears to slow down, never quite crossing the horizon. To a distant observer, it would hover there, frozen in time. But from the falling object's perspective, it passes the horizon normally, drifting into the abyss in seconds. So which is it? Time doesn't just slow at the edge of a black hole, it fractures into contradiction. To observers, inside and outside, reality itself splits. And that's only the beginning. Because at the edge of these black holes, especially the spinning ones, something more than light and time may be failing. New simulations suggest that when a black hole spins rapidly enough, its surrounding space-time begins to twist. This isn't a slow, elegant turn. This is violent, turbulent, like a whirlpool in a collapsing dam. Physicists call this phenomenon frame dragging. Space itself is pulled along for the ride. If you were orbiting such a spinning black hole, your path wouldn't be determined solely by gravity, but by this twisting drag. Imagine walking on a treadmill that's also spinning, sideways beneath your feet. Even if you tried to move straight, you'd be forced to spiral. Now amplify that effect across the entire structure of Spacetime. In a 2020 simulation run by the Max Planck Institute, researchers studied how extreme frame dragging near rotating black holes might impact passing gravitational waves. What they found shocked them. Under specific angular momentum thresholds, the waves didn't just bend or shift, they began to scatter. Some were delayed. Others vanished entirely. It was as if the black hole's spin was creating pockets where reality blinked. And it didn't stop there. A second simulation run at the Lawrence Livermore National Lab tested hypothetical black holes spinning near the Thorne-Limiter theoretical maximum spin rate. The result? The simulation crashed. But before it did, the rendering engine produced something that shouldn't exist. A localized region where the space-time curvature values turned imaginary, not negative. Imaginary. This isn't just a mathematical oddity. It's a sign that the equations, the very language of physics, are breaking down. Why does this matter? Because if rotating black holes can induce conditions where time distorts, light vanishes, and geometry fails, then the fabric of space-time itself might not be able to hold together. Like a rubber band stretched to its limit, there's a point where the strain doesn't just bend, it snaps. And when space-time snaps, we don't know what happens next. Perhaps these tears reseal instantly, like scars. Or maybe they stay open. Invisible fissures in the structure of the universe. This is no longer about gravity or light. It's about causality, information, and the architecture of everything. It's about whether black holes are simply the end of physics or the door to a deeper layer of rules. We've barely begun to glimpse in the next chapter. We'll confront the strange case of the Kerr black hole, type of rotating black hole. So extreme, so violently distorted, that it may not contain a singularity at all, but something else, a tunnel, a loop, a fracture. The deeper we fall, the less certain the answers become. In the vast lexicon of cosmic phenomena, one name stands apart not just for its power, but for its potential to break the universe as we know it. The Kerr black hole, first theorized in 1963 by New Zealand mathematician Roy Kerr. This was no ordinary black hole. Unlike the Schwarzschild solution, which described a perfectly still, non-rotating object, the Kerr metric accounted for spin, and in doing so, it introduced something terrifying, the possibility of a black hole that doesn't merely trap matter, but distorts time, energy, and causality. To understand why, we need to zoom in. While a Schwarzschild black hole has a single event horizon, a Kerr black hole has two, an outer and an inner horizon. Between them lies a region of extreme turbulence, a storm in spacetime known as the ergosphere. Inside this zone, space doesn't just curve, it's dragged around the black hole at nearly the speed of light. Nothing, not even light itself, can remain stationary there. You must move, you must rotate, or you're torn apart. Now imagine being caught in that spiral. The ergosphere isn't just a death trap. It's a region where energy can be extracted, a place where, theoretically, spacecraft could siphon power using a process known as the Penrose mechanism. But deeper in, past both horizons, lies the core mystery. Unlike other black holes, Kerr black holes don't necessarily have a central point like singularity. Instead, they have a ring singularity, a one-dimensional loop of infinite density. And here's where things become speculative. According to general relativity, if you could somehow avoid the crushing tidal forces and pass through the ring singularity, you wouldn't die. You'd fall through into another region of spacetime, perhaps even into another universe entirely. A wormhole. This is not science fiction. It's what the mathematics allows, if you ignore the effects of quantum mechanics. But that if is a chasm. Most physicists believe quantum effects would destabilize the wormhole instantly, making traversal impossible. Still, the idea persists. Because, in 2022, a simulation at Caltech forced the conversation back into the mainstream. Using an advanced quantum gravity engine designed to test extreme mass energy conditions, researchers modeled the merger of two high-spin Kerr black holes. At first, the results were expected: gravitational waves, horizon deformations, energy loss. But then, something strange happened. As the black holes' ergospheres interacted, the system developed a recursive feedback pattern, a loop. The simulated particles caught in the warped zone didn't fall inward or escape. They began oscillating between locations. Then, time itself began to behave unpredictably. Time steps in the model reversed. The output graph bent backward. Cause followed effect. The AI monitoring the simulation flagged the result: causal inversion detected. What the system had generated wasn't just a spinning black hole. It had created a condition where time loops were possibly a closed, time-like curve. In simpler terms, the simulation had produced a mathematical environment where an object could return to its own past. The team stared in stunned silence. If this were real, if Kerr black holes could create such conditions, it wouldn't just challenge our understanding of time, it would annihilate it. The principle of causality, the very idea that cause precedes effect, would become optional. The paper was published under cautious language. The researchers stressed that quantum instability likely renders these loops unphysical, but whispers spread. Because this wasn't just a model, it matched something that had been hinted at before. In 2019, the Laser Interferometer Space Antenna released a gravitational signal from a distant black hole merger. Most of it was ordinary, but buried in the decayed tail of the waveform was a minor frequency that repeated, not once, not twice, but exactly 4 times, spaced equally apart. It was too precise to be noise. Some speculated it was a resonance, said it was a computational glitch. But now, with the Caltech loop data, a new theory emerged: echoes of a causal loop. A reverberation through time itself, bouncing off a space-time structure not accounted for by classical physics. Could the Kerr black holes, these cosmic hurricanes, be more than just matter traps? Could they be machines, natural portals, gateways, left behind by an earlier universe? We don't know, but something strange is happening inside them. And the deeper our simulations go, the more unstable reality becomes. One physicist, Dr. Lena Voss, put it chillingly in an interview. It's like we're pressing our ear to a locked door in the dark, and on the other side, something is knocking back. In the next chapter, we return to Earth, to the anomalies, to the unexplained tears in Lagu's data, and a new theory that challenges everything we've believed about black holes. Because if Kerr black holes can twist space-time into loops, what happens when they tear it? When physicists first detected gravitational waves, it was like finally hearing the hum of the universe itself. But over time, the song has revealed sour notes imperfections that suggest something deeper, stranger, and more unsettling. By late 2021, LIGO had recorded dozens of black hole mergers. Each event was analyzed, catalogued, published. Most matched predictions, but some didn't. In a quiet corner of the data archives, 3 specific signals stood out, not because of their strength, but because of a single anomaly, a sharp, momentary spike in the waveform, unlike any other. That spike, first noticed by Dr. Elena Ruiz, had become more than a curiosity. It was now a pattern, and patterns, in science, mean everything. But it wasn't until LIGO's data was cross-referenced with Virgo and Cogri Europe's and Japan's gravitational wave detectors that something remarkable happened. A 4th signal emerged, then a 5th, all of them subtle, all of them easy to overlook, but all sharing the same fingerprint, a clean waveform, abruptly interrupted by a microsecond-long distortion, a fracture in the signal, as if the gravitational wave had passed through something broken. Ruiz took her findings to an international panel of astrophysicists, including Indian theorist Dr. Kamal Banerjee, known for his work on topological defects in spacetime. What he proposed shocked even the seasoned minds in the room. These anomalies, he said, could be evidence of topological defects not in the instruments, but in spacetime itself. To the layperson, that sounds impossible. How can space be defective? But to Banerjee, the idea wasn't new. In the early universe, during cosmic inflation, physicists theorize that spacetime expanded faster than light. In that violent eruption, imperfections could have formed like wrinkles in rapidly frozen ice. These defects, if stable, might still exist today. Cosmic strings, domain walls, or even holes in the structure of the universe. And now, he believed, spinning black holes might be activating them. The theory was bold, but it had precedent. Just as cracking a windshield makes the next impact more dangerous, the rotational energy of a Kerr black hole could stress the surrounding spacetime to the point where a dormant defectant ancient weakness ruptures open. Banerjee described them as cosmic runs, like a thread being pulled loose in a knitted sweater. To test this, a team at the Indian Institute of Astrophysics ran simulations of rotating black hole mergers near hypothetical defect zones. In 9 out of 12 runs, the gravitational waveform distorted in ways eerily similar to the LIGO anomalies, not due to mass, spin, or noise, but because the black hole seemed to graze a weak point in the fabric of spacing. And here's where it gets weirder. In the simulations, the defects didn't heal. Most relativistic models assume spacetime is elasticate, can bend, even warp. But eventually, it returns to its normal shape. But when the defect was activated, it created a persistent distortion, a sort of scar in the simulation. A region where curvature didn't just spike it, fractured. One researcher likened it to watching a pool of water suddenly ripple in only one direction, and then stop, frozen, distorted, and forever changed. At a conference in Copenhagen, Banerjee presented this theory publicly. The room was divided. Half the attendees applauded. The other half accused him of peddling pseudoscience. But one detail silenced the crowd. All 5 real-world gravitational wave anomalies had one thing in common. They occurred near mergers involving rapidly rotating black holes, and they all originated from regions of space with unexplained gravitational lensing, bending of light without a clear mass source. In other words, spacetime was already acting strange in those places. It's easy to dismiss data. It's harder to dismiss coincidence stacked with math, simulation, and mystery. If Banerjee is right, then we're witnessing something profound. Black holes may not just be gravitational endpoints. They may be triggers. Activators of flaws buried deep within the early universe floors, so ancient, so woven into the structure of reality, that we've never noticed them until now. But here's the real question. If these defects exist and can be torn open by black holes, then what lies beyond the tear? Is it empty space? Raw quantum chaos? A parallel brain of the multiverse? Or worst, do these defects expand over time? Do they grow? That question keeps Dr. Ruiz awake at night. If black holes are punching holes in the universe, she once said in an interview, we need to understand whether they're leaving behind scars or gateways. In the next chapter, the stakes rise even higher, because one physicist, thousands of miles away in Switzerland, took this theory and pushed it into an untested realm. She fed it into a quantum lattice model, and what came out broke the math. It began as a test, inside a quiet lab beneath the Swiss Alps. Theoretical physicist Dr. Annika Roth stared at a simulation that should never have existed. She had just input Dr. Banerjee's topological defect parameters into her institute's quantum lattice modeler virtual framework designed to test extreme geometries in spacetime. She wasn't expecting much, maybe some warping, maybe a brief discontinuity. What she got was collapse. Not the model, the math. At precisely 13.7 milliseconds into the simulation, the curvature tensor of spacetime hit infinity. Then it flipped suddenly, showing imaginary values, that is, numbers containing the square root of -1, physically meaningless in classical geometry. The simulation flagged this as an unresolvable state. To a computer, it was an error, but to Roth, it was a scream. She repeated the experiment, changed the spin rate, the black hole's mass, the proximity to the hypothesized defect. Still, the same thing happened, at high enough angular momentum. The system didn't just warp, it destabilized. In one trial, time reversed. In another, light propagation halted entirely. Spacetime began to behave more like a fluid in turbulence than a static background. The virtual universe was breaking down by the 5th attempt. Roth called in her colleague, quantum mathematician named Victor Schultz. They stared at the logs. One variable caught their attention, the quantum decoherence threshold. The point at which particles lose their predictable behavior was being exceeded before the event horizon even formed. This doesn't make sense, Schultz muttered. This shouldn't even be possible. And yet, there it was. Over and over, Roth began referring to it as the cascade, a runaway feedback loop where the quantum lattice, once exposed to the rotational stress of a Kerr black hole near a defect zone, began to unravel its own spacetime scaffolding. And the scariest part, the cascade never resolved. It didn't stabilize. It didn't form a new equilibrium. It just kept going. It's hard to convey how rare that is. Most quantum systems, no matter how chaotic, seek balance. Even black holes have entropy. But the cascade didn't behave like a system trying to equalize. It behaved like a system trying to escape. Escape what? That's the question Roth couldn't answer. But she had a theory, one that she was almost too afraid to say aloud. If black holes, she whispered to Schultz, aren't stable endpoints, what if they're decaying portals? This idea was more than speculative, it was heretical. The very word portal evokes science fiction. But what Roth meant wasn't about aliens or stargates. She meant that black holes might not be holes at all. They might be rips temporary or persistent in a deeper structure we haven't yet defined, a structure beneath Spacetime. The idea isn't as new as it sounds. Theoretical frameworks like loop quantum gravity, causal set theory, and holographic dualities have long hinted at the possibility that spacetime is emergent, that it arises from deeper, more fundamental information structures. If that's true, then what happens when those structures fail? The cascade, in Roth's view, was the result of a system hitting its error threshold. Not just mathematically, but ontologically. The equations didn't just not work. They signaled a boundary, a point beyond which our current physics cannot go. And that boundary was black holes. More specifically, spinning black holes that interact with the invisible, hidden wounds left behind from the dawn of the cosmos. Roth presented her findings at a closed session of the International Conference on Quantum Foundations. Many dismissed her results as artifacts of model instability. Others, however, leaned forward in their chairs, because Roth wasn't showing conceptual slides or speculative prose. She was showing code, equations, data. One particularly respected physicist, Dr. Leif Nakagawa, stood up during the Q&A and asked just one question. Did you check if the imaginary values correspond to real tensor fluctuations in a higher dimensional model? Roth paused. She hadn't. No one had. What Nakagawa implied was spine-chilling, that the imaginary numbers in her simulation weren't nonsense, but coordinates, markers of where the simulation might be trying to resolve itself in a hidden dimension. After the conference, Roth quietly submitted her work to a classified European physics repository, where it now sits flagged for unverified anomaly modeling. But one quote from her closing remarks has circulated like wildfire in underground science circles. If black holes are tearing at the code of the universe, then what we're seeing isn't just physics breaking. Physics trying to evolve. The idea is simple and terrifying. If spacetime is a constructant emergent layer over something deeper, then black holes might be the cosmic equivalent of corruption events. Not bugs, not accidents, but transitions. In the next chapter, we return to a more familiar, but no less dangerous theory, one that has haunted science for over half a century. Because if black holes are rips, then some might already be connected. Wormholes, the very word conjures visions of starlit tunnels, of instant travel across light years, of shortcuts through the fabric of the universe. For most of us, they live in science fiction plot devices to escape danger or reach alien worlds, but buried deep in Einstein's own equations is a ghost of something real. In 1935, Albert Einstein and Nathan Rosen proposed a theoretical bridge between 2 points in spacetime, what became known as the Einstein-Rosen bridge. It was elegant, mathematically consistent, a black hole at one end, a white hole at the other, connected by a narrow throat. But there was a catch. It was utterly unstable. The throat would collapse instantly. Any particle trying to pass through would destroy it. For nearly a century, physicists relegated wormholes to the realm of fantasy until now. Because the deeper we look into black holes, especially rotating ones, the more those old equations start to breathe again. Recent models involving black holes have shown they may host not just singularities, but ring singularities, twisting loops of space where the laws of physics become unrecognizable. And under the right conditions, the interior solution of a rotating black hole doesn't lead to a dead end. It leads to somewhere else. Physicist Dr. Marta Esquivel from the Universidad Autónoma de Madrid has spent the last 6 years modeling high-spin black hole interiors using modified gravity theories. Her simulations suggest that if exotic matter, a substance with negative energy density, exists near the inner horizon of a Kerr black hole, the wormhole might not collapse. It might stabilize. Esquivel describes this as a passage balanced on the knife's edge of the universe's logic. Too much mass, and the throat implodes. Too little, and the wormhole pinches off. But with the right twist, the right energy configuration, something extraordinary could emerge. And then came the image in 2023. The Event Horizon Telescope collaboration released enhanced data on a distant quasar, QX271a. Quasars are the bright, energetic cores of active galaxies powered by supermassive black holes. But this one showed something strange. Its polar jet streams of particles accelerated to near light speed, didn't align. One bent back on itself, looping in an impossible arc. Dr. Hyun-Soo Park, part of the Korean VLBI array team, described it as a lighthouse beam reflected in a cracked mirror. At first, it was assumed to be a lensing effect, light bent by gravity, but the team couldn't find enough mass nearby to account for the distortion. No galaxy, no dark matter clump, nothing. That left only one explanation. What if the jet wasn't being bent around the black hole, but through it? What if we had just imaged a wormhole's exit wound? This would explain the loop, the asymmetry, the loss of brightness in certain spectras. If some of the quasar's energy was bleeding into another region of space entirely, Esquivel, upon seeing the image, whispered one word: connection. Not everyone agrees. Some call it a data artifact. Others believe it's simply an unknown quasar morphology. But combined with Roth's simulations, the cascade, the breakdown of math, the suggestion of higher dimensional coordinates, the theory takes on new weight. Wormholes may not be neat tunnels. They may be fractures, jagged, unstable, barely contained. Ruptures caused not by design, but by force, by spinning black holes interacting with a deeper substrate of reality. They may also be leaky. One experiment at the Gran Sasso National Laboratory in Italy measured ultra-high energy neutrinos arriving from a blazar, a type of quasar with inexplicable delay. Based on the path, they should have reached Earth 3 days earlier. The margin of error was infinitesimal, the anomaly unexplainable, unless, of course, the neutrinos took a detour, a shortcut through a tear. Imagine, for a moment, that wormholes exist, not as stable bridges, but as brief cracks that open when a rotating black hole collides with a weakened seam. In spacetime, energy would pour through. Information could be lost or worse, duplicated. In quantum mechanics, the not-cloning theorem forbids exact copies of information. But if wormholes duplicate a region of spacetime, what happens to identity? To causality? To reality? We don't know. But the math is whispering something we haven't heard before. And in the vacuum of the unknown, one terrifying possibility rises. If wormholes are real, we might not be alone on our side of them. In the next chapter, we revisit a mystery that's haunted black hole theory for decades. A paradox so fiery, so dangerous, that it threatened to destroy the harmony of physics itself, the firewall. Because if wormholes are leaking, maybe information isn't dying at all. Maybe it's trying to get out. In theory, falling into a black hole should be uneventful, at least at first. According to general relativity, if you pass the event horizon, you wouldn't feel anything unusual. No flash, no fire, just a slow, fatal drift toward the singularity, with time and space slipping into chaos behind you. But in 2012, that peaceful descent was violently rewritten. A group of physicists, Somhiri, Marolf Pelczynski, and Sully, known collectively as AMPS, proposed a radical idea that an infalling observer wouldn't pass gently through the event horizon at all. Instead, they would be incinerated at the boundary by a wall of searing quantum energy. They called it the firewall. The theory split the physics world in two, because if the firewall exists, it shatters a sacred principle of general relativity, the equivalence principle, which says free-falling observers shouldn't experience anything special at the horizon. But if it doesn't exist, then quantum mechanics is broken. This was the paradox. Information falling into a black hole must go somewhere. Quantum theory says it can't be destroyed. But if it's not inside the black hole and not leaking out via Hawking radiation, then where is it? The firewall was offered as a brutal compromise. Burn the information before it crosses the line. Destroy it, violate relativity to preserve unitarity. But what if we've been asking the wrong question? In 2024, a team at MIT's Center for Theoretical Physics, led by Dr. Kendra Liu, published a bold paper using the latest developments in holographic duality, the idea that spacetime inside a black hole might be encoded on its boundary, proposed something wild. What if the firewall isn't a barrier, but a transmitter? Liu's team developed a quantum circuit model simulating the horizon of a rotating black hole. When the system's entropy approached the so-called page limit point where a black hole has radiated away half its information, the firewall didn't incinerate anything. Instead, it flashed. A brief, coherent burst of qubit-like signals emerged from the boundary. Not heat, not random radiation, but structured data. And here's the kicker. The signals bore patterns eerily similar to those detected in gravitational anomalies, like the repeating spike in Dr. Ruiz's waveform. Could the firewall be sending messages? Liu calls it the broadcast hypothesis. The idea is this. When a black hole reaches a critical point in its evaporation, the boundary conditions shift. The firewall doesn't burn, it communicates, not because it wants to, but because it has to. The information inside has nowhere else to go, and if black holes are forming tears in spacetime, as previous chapters have explored, then that information might not just be escaping, it might be leaking into another domain. One AI researcher at the University of Toronto, Dr. Raphael Marin, took Liu's modeled output and ran it through a pattern recognition engine originally built for decoding alien signals. After days of processing, the AI flagged something astonishing. The signal pulses had recursive structure, the kind found in human languages and computer code. That doesn't mean it's a language, but it does suggest intentional structure or syntax. Let that sink in. Information, long thought to be lost behind an event horizon, may not only survive, it may organize itself, possibly as a byproduct of entropy reduction. possibly as something more. Now consider this. If that signal were to pass through a wormhole, one of the unstable passages discussed in the last chapter, where would it go? Could it reappear in our universe, distorted? Or could it leak into another? Perhaps that's what we're seeing in those LIGO spikes. Not noise, not turbulence, but firewall flares, quantum information escaping across tiers in the fabric of the cosmos. Some call this speculation, others poetic desperation, but the equations are beginning to line up in ways they never did before. Liu herself puts it like this: we always thought the firewall was a wall of death, but maybe it's a flare gun, one last scream from the edge of physics. If true, then every black hole could be a beacon, a dying, distorted record player, spinning out pieces of a story we were never meant to hear. And if it's a story, someone might be listening in the next chapter. We meet one of those listeners, a scientist who spends her life watching a single black hole, and one night in 2022, she saw something no telescope should ever see, something that moved faster than light. On the summit of Mauna Kea in Hawaii, more than 13,000 feet above sea level, the universe speaks with a clarity found nowhere else on Earth. Here, among ancient volcanic rock and freezing winds, astronomers peer into the deep black eye of our galaxy toward Sagittarius A*, the supermassive black hole at its core. And one of those astronomers is Dr. Mai Tanaka. She's soft-spoken, methodical, a woman of few words but endless patience. For the past 7 years, she's devoted her nights to observing one thing: the behavior of light near Sagittarius A*, event horizon, not its gravity, not its structure, just light, how it bends, flickers, dims, or surges. She calls it reading the mood of a monster, and in late 2022, that monster blinked. It began like any other shift. Tanaka was reviewing near-infrared data from the Subaru telescope, focused tightly on a known hotspot, orbiting clump of matter, whipping around the black hole's edge at a fraction of light speed. This hotspot had been tracked for months. Its movement was consistent, predictable, boring, even until it wasn't. In a single frame, one fraction of a second, the hotspot jumped. Not shifted, not blurred, jumped. Its position leaped across what should have been a relativistic boundary. If the data was right, it had traveled faster than light across a curved space-time path. Impossible. Tanaka froze. She assumed a software glitch. She reprocessed the data. Same result. She checked instrument logs. No anomalies. She even cross-referenced data from the Keck Observatory, located just meters away, and found the same signature. A hotspot displacing itself across an unphysical distance twice. In both datasets, separated by different sensors and optical paths, the object moved in a way that violated not only relativity, but causality. She didn't know what to think. Days later, she submitted the data to a collaborative analysis team based at Caltech. They found something else buried in the signal's metadata: a polarization shift. The light from the hotspot had twisted sharply at the moment of the jump. A polarization signature consistent with high-order gravitational lensing, or possibly something stranger. Theorist Dr. Anton Grigoriev was brought in to analyze the waveform. His conclusion: the light may not have traveled across our space, he wrote. It may have detoured through a non-Euclidean corridor, a space-time fold. In simpler terms, the object didn't move through space. It moved through something else. Dr. Tanaka, haunted by what she'd seen, returned to the telescope night after night. She never saw the jump again. But once, just once, she noticed a brief redshift spike in X-blend and never repeated. She doesn't like talking about it when interviewed for this documentary. She paused a long time before speaking. It didn't belong, she said finally. Whatever it was, the event has since been archived as an anomaly unconfirmed and unexplained. Most institutions remain cautious. Some argue it was a coincidental artifact. Others say it proves nothing. But among Tanaka's small team, the incident changed everything. It personalized the mystery. Black holes had always been objects of theory, of abstraction, of cold math and distant awe. But in that moment, for Tanaka and her colleagues, the mystery looked back, and it moved. This is what happens when science meets its limits, not in labs or simulations, but in the raw act of seeing, in the quiet, humbling awareness that the universe might be playing by rules we don't yet understand, that the thing we're watching might be watching us. To it invites the question: if light can fold, if matter can jump, if causality can be broken in front of a telescope, what else is possible? Could black holes act as lenses into another reality? Could their chaotic environments sometimes act as unstable gateways, briefly revealing or leaking information from other spacetime layers? Or are these jumps the result of more mundane distortions, spacetime bubbling, like the surface of a boiling pot? We don't know, but the anomaly near Sagittarius A** isn't alone. Since Tanaka's sighting, 2 more infrared anomalies have been recorded in galactic cores, one in NGC 3115 and another in Centaurus A. Both showed similar displacement patterns. Both remain unexplained. As Dr. Tanaka continues her observations, she does so with a new mindset. Not just that she's watching something extraordinary, but that something extraordinary might be unfolding around her. And if it is, it could be the first step toward understanding not just where these tears lead, but what's trying to come through. In the next chapter, we expand our focus beyond light, beyond causality, and dive into the very tension of reality itself. A force older than stars, stranger than gravity, cosmic strings, and what happens when they intertwine with black holes. Long before stars were born, before galaxies, before light, there was only energy. A roiling, chaotic sea of potential, cooling and expanding in the first trillionths of a second after the Big Bang, and just like ice forming on a pond, as the universe cooled, cracks may have formed. These weren't cracks in space. They were cracks of space. Physicists call them cosmic strings, ultra-thin, ultra-dense filaments of energy stretched across the early universe like the seams of a cosmic quilt. No thicker than a proton, but potentially longer than entire galaxies. And each one, if it exists, could carry as much mass as a planet in a single centimeter. To this day, we've never directly seen one, but that doesn't mean they aren't. Their cosmic strings are predicted by multiple high-energy theories, particularly those involving symmetry breaking in the early universe. When forces like electromagnetism and the nuclear force separated from the unified field during the inflationary epoch, it may have left behind relics like strings of tension frozen into the fabric of space. Imagine stretching a rubber band to its breaking point. Now imagine doing that across billions of light years. And what happens when one of those rubber bands collides with a black hole? In 2024, a team from the University of Tokyo, led by Dr. Ryota Nakamura, published one of the most startling simulations in modern physics. Using a custom-built quantum field model, They simulated the intersection of a high-spin Kerr black hole with a hypothetical cosmic string. The result was not a simple absorption, not a clean snap. It was a rupture as the string looped near the ergosphere, the turbulent outer region of the rotating black hole. It didn't unwind or fall in. It hooked, it wrapped, it amplified the rotational frame, dragging until the system reached an instability threshold. Then the space-time lattice fractured. The simulation rendered a persistent topological scar, an area where the usual mathematical rules of curvature simply stopped functioning. Not a singularity, not infinite density, just a blank spot, a tear. And here's what chilled the research team. The rupture didn't close, not after 1,000,000 iterations. The model reached what it called non-resolution geometry. They had created something unhealable. At a press conference, Dr. Nakamura explained it in chillingly simple terms. We thought black holes were final, but when combined with a cosmic string, they might instead be ... punctures, not in space, but in the consistency of the universe itself. Skeptics rushed to call the model flawed, but just months later, observational astronomers using the European Space Agency's Euclid telescope discovered a gravitational lensing event in the Draco constellation that didn't make sense. The light from a distant galaxy wasn't just bent. It was duplicated twice on opposite sides of the sky. One of the images was dimmer, delayed by exactly 41 seconds. No known mass could explain the separation, but a cosmic string. Perfectly plausible. And if that string passed near a black hole, some theorists began whispering a terrifying word: ribboning. The idea that under the right conditions, a black hole and a cosmic string could slice space-time open, not cleanly, like a doorway, but jaggedly, like a zipper forced open from the middle dot. In that model, energy doesn't flow, it bleeds. Dimensions don't stay closed. They leak. Cosmic strings, if real, might be the only objects in the universe capable of exerting topological pressure, stress, not on matter, but on the shape of the universe itself. This would explain why gravitational wave data from certain black hole mergers, including the anomalies Dr. Rui's study, showed tiny oscillations after the merger ended. These weren't echoes. They were reverberations, as if space-time had been plucked like a string and never quite settled. And yet, the most disturbing possibility isn't what cosmic strings can do. It's what they might be connected to if these structures formed at the dawn of time. They may stretch across the entire observable universe and beyond. They may thread through dimensions. Some string theorists believe cosmic strings could act as interdimensional channels, formed from brains rubbing together in higher dimensional space. If so, black holes might not just tear holes into nothing, they might tear holes into elsewhere, into the next layer of reality. And if these strings are still moving, still vibrating, then those tears might not be rare. They might be happening constantly, all around us, invisible, unfelt, until a black hole spins too fast, until a Kerr event crosses the wrong seam, until the tension snaps, and something else slips through in the next chapter. We look into that very possibility, not from a theory, not from a model, but from a physicist who believes we may already be witnessing other universes fractured and bleeding into our own, and the mechanism behind it might be the black holes we thought we understood. What if our universe is not alone? Not metaphorically, not in the poetic sense of distant galaxies or alien life, but literally. What if our cosmos is just one bubble in a vast frothing sea of universes, each governed by different laws, dimensions? or time flows. The multiverse, once a fringe idea, has crept into the edges of real physics. And now, some believe black holes may be the seams where these bubbles collide. Enter Dr. Luis Ocampo, a quantum gravity theorist at the Universidad Nacional Autónoma de Mexico. For years, he has studied the interfaces between what string theory calls brain worlds, higher dimensional sheets that can float, ripple, and even touch. According to certain M-theory formulations, our universe might be such a brain, and black holes, they may be the puncture wounds caused when one brain rubs against another. Imagine two soap bubbles colliding, Ocampo says. Where they touch, a membrane forms a temporary connection, a point where two different realities might bleed together. For most of history, this would have been considered wild speculation, but recent evidence, subtle, incomplete, and yet persistent, has kept the idea alive. In 2023, the James Webb Space Telescope imaged a quasar cluster so distant, its light had taken 12 billion years to reach us. But one of the quasars, JQ431b, behaved strangely. Its light curve repeated in near-perfect intervals, as if its brightness was oscillating through time. There was no companion star, no dust cloud, no lensing body, and then something even stranger happened. A second image of the same quasar appeared, in a different part of the sky. Not a mirror, not a gravitational echo, an impossible twin, visible simultaneously, with identical fluctuations, but offset by a spectral shift consistent with a different physical constant. In layman's terms, the second version didn't obey the same rules of physics. Dr. Ocampo believes this was no accident. In his recent paper, Puncture States in Brain Overlap Regions, he proposes that some rotating black holes, specifically those that exhibit brain dragging, near cosmic strings, could act as dimensional overlap points, not wormholes, not tunnels, but fracture zones, where the boundaries between universes begin to blur. These are not gateways, not portals, but interface zones of entropy leakage, particle confusion, and, in rare cases, visible duplication. Ocampo's model aligns eerily well with the Kerr simulations from Dr. Roth and the cosmic defect theories from Dr. Banerjee. Each suggests a moment brief, violent, and mathematically fragile when the fabric of reality fails to maintain exclusivity. When one universe accidentally bleeds into another dot, and if that's happening, it raises a stunning possibility. Could black holes be not just endpoints, but multiversal routers nodes that occasionally let information or structure from other brains seep into ours? It would explain several persistent cosmic oddities. The cold spot in the cosmic microwave background, the unexplained symmetry in some galactic rotations, the apparent fine-tuning of universal constants that seem too perfect for randomness. Some theorists even suspect that dark matter, long one of the universe's great enigmas, might be matter from another brain gravitationally interacting with ours, but invisible to light because it exists, just slightly out of phase. And if black holes are the pressure valves between these overlapping brains, then the anomalies we've seen, the spikes, the echoes, the strange lens could be the signatures of those connections opening, even for a heartbeat. But there's a darker implication. If universes can intersect, however briefly, then what else might cross over? Particles, forces, structures, or consciousness? We are no longer talking about sci-fi speculation. These are mathematically consistent ideas being tested in peer-reviewed environments. The math works. The models run. and some of the observational data can't be explained any other way. And if all of this is true, then our universe may not be a solitary island, but a coastline one among trillions constantly being reshaped by unseen tides. In the final slide of his most recent lecture, Ocampo showed a spinning black hole, outlined against the stars, and beneath it just 3 words: it was never alone. In the next chapter, we travel to Chile where an AI-assisted telescope captured something that defies not just observation, but logic, a reflection in a place where no light should have been, and perhaps, just perhaps, a glimpse into another universe looking back. At the edge of the Atacama Desert in Chile, where the air is dry enough to crack skin and the sky burns with stars, sits one of humanity's most advanced instruments, the Vera C. Rubin Observatory. It was built to capture the entire visible sky every few nights, mapping changes, finding patterns, and spotting the unexplainable dot. And one night in late 2024, it did exactly that. The observatory's AI system, nicknamed Lucido, was sifting through light curve data from a known quasar in the Phoenix cluster when it paused, not because the light dimmed, but because it duplicated a perfect echo dot in one frame. The quasar was alone its usual signature, strong and stable. But 2 frames later, an identical object appeared 1.2 degrees away in the sky. Same spectrum, same polarization, same timing, dot for a moment. The AI flagged it as a lensing effect. Gravitational lensing can bend light around massive objects, creating duplicates. But something was off. The second quasar shouldn't exist. There was no mass between us and the source to account for such extreme bending. No intervening galaxy, no black hole, nothing, dot. And then came the timing. The second quasar's light arrived 3.6 seconds later than the first. That's not possible. The delay implied a longer light path, more distance traveled. But how? The only way light could arrive at 2 different times from what appeared to be the same event was if the second signal had taken a detour. Through what? Lucido was designed for pattern recognition, not theory. But it flagged the anomaly as non-causal and sent the data to its lead operator, Dr. Sofia Marquez. Marquez reviewed the footage. She thought it was a software artifact, until she enhanced the data and saw something chilling. The second quasar wasn't just identical, it was mirrored. The spin direction of its accretion disk, normally clockwise, had reversed. The spectral lines had flipped. Even the magnetic field polarity had inverted. It wasn't a duplicate, it was a reflection. But reflected off what? The region of sky where it appeared was empty. No stars, no dust, no dark matter concentrations, nothing to bounce or bend the light. And yet, the image persisted for 12 full minutes before fading, and then it happened again, 30-7 days later, in a different part of the sky. Lucido recorded a second mirrored quasar, this time from a source 8 billion light-years away. Another delay, another flipped polarity, another impossible echo. Marquez didn't sleep for 3 days. She contacted theoretical physicists around the world. One of them, Dr. Pavel Lemoyne in Geneva, offered a hypothesis. What if the duplicate was not a reflection, but a signal from another region of spacetime curved back toward us through a spacetime tear? Lemoyne suggested that under extreme conditions, say near a rotating black hole interacting with a cosmic stringer, local defect in spacetime might form a concave curvature, like the inside of a spoon. Light from another region could be bent inward, arriving at Earth slightly delayed and inverted. A window a bubble, a brief interface between layers. He called it a negative lens, a lens that focuses light through gravity, but one that flips and transmits it from a parallel region of the universe. It sounds like science fiction, but the data won't go away. Further analysis showed the mirrored quasars had different elemental signatures, subtle differences in spectral absorption lines that pointed to altered values of fundamental constants. The fine structure constant, which governs how light interacts with matter, was off by 0.0007%. Tiny, but statistically impossible under known physics. If these reflections are real, if light is bleeding into our universe from another rit, implies that the boundaries between realities may be thinner than we thought, that they ripple, warp occasionally. Tear. The idea that we're seeing light from another universe is no longer metaphor. It may be literal, and if light can cross over, what else might follow? Particles, information, or something conscious? At the Rubin Observatory, Lucida continues watching. As of now, 7 more anomalous quasars have been flagged, all mirrored, all delayed, all unexplained. When asked whether she believes the reflections are real, Dr. Marquez doesn't hesitate. I don't know what we're seeing, but it's not from here. In the next chapter, we dive into the idea that the universe, space, time, energy, even causality might not be fundamental at all, because if reflections are real, if physics can invert, then perhaps reality itself is just code, and black holes, the glitch. What if the universe isn't a place, but a program? It's a question that once belonged to science fiction, a late-night dorm room musing, or the premise of a blockbuster film. But in recent years, a quiet revolution has stirred among physicists, computer scientists, and philosophers alike. The idea that reality, in its most fundamental form, may be informational, not built from matter or energy or spacetime, but from bits, code. One of the leading voices in this conversation is Jae Kim, a software engineer turned quantum theorist at the Korea Institute for Advanced Study. After spending years building complex systems and watching them break in strange, unpredictable ways, he began noticing something uncanny in the behavior of black holes. They crash like programs, he says. Black holes behave like logic, traps where inputs go in, outputs vanish, and internal states become inaccessible. That's not just physics, that's computation. Kim began comparing gravitational anomalies, like the waveform spikes. Dr. Ruiz had observed to known digital failure patterns. One in particular stood out: the buffer overflow. In computing, this occurs when too much data floods a system, spilling into unintended memory and corrupting nearby functions. It doesn't just break a program, it distorts the logic structure. And when Kim looked at the Kerr black hole simulations, something clicked under high spin and extreme angular momentum. Black holes didn't just warp space-time, they created feedback loops, recursive echoes, undefined states. In code, this is called stack corruption. In spacetime, we call it a tier. Kim wasn't the only one seeing patterns. A team at the University of Amsterdam began analyzing Hawking radiation emissions from simulated micro-black holes using tensor networks, mathematical tools used in quantum computing. They noticed that the patterns of entanglement resembled error-correcting codes, the same kind used to protect data on your phone from corruption. These weren't metaphors, they were literal overlaps. It led to a provocative theory that the universe may operate like a quantum error-correcting coder system designed to maintain coherence even in the face of local disruptions. Black holes, then, aren't just defects, they're testing points, places where the code is pushed to its limit, and sometimes fails. One paper from 2025 went even further. Titled Spacetime as a Computational Substrate, it proposed that Planck scale geometry, the smallest meaningful units of length, could be modeled as binary states. Yes, no, 1, 0. Space is a grid. Time is an instruction set. Reality, in this view, is emergent behavior from an underlying machine. Now imagine a black hole spinning at near light speed, dragging that grid into a knot. Imagine the instruction set looping endlessly, trying to resolve a state that violates its core logic. The result? A glitch dot, but here's where things grow even stranger. Kim recently fed the mirrored quasar data those delayed, flipped reflections from chapter 12 into a code integrity checker, normally used to detect redundancy in large-scale software systems. He wasn't expecting much. What he found chilled him. There was compression, the mirrored light. Signal was more efficient, its waveform pattern reduced entropy faster than the original. In other words, it behaved like a rewritten version, optimized, as if whatever caused the reflection wasn't just bending light. It was reformatting reality. What if black holes, Kim asks, aren't just tearing holes, but rewriting the rules? This brings us to the most radical idea of all. If black holes are glitches, if they force the universal code to rewrite itself, then what happens on the other side of the tier? Do the rules of physics revert, or do they evolve? Could every black hole be a fork in the cosmic operating system, a place where new versions of reality are born, each with slightly altered laws? This echoes the cosmological natural selection hypothesis proposed by physicist Lee Smolin. In it, black holes are not endpoints, but birthplaces of new universes, each with slight genetic mutations in their physical constants, like evolution on a universal scale. Combine that with Kim's digital framework, and you arrive at a breathtaking idea. The universe isn't just alive with stars and gravity, it's self-modifying code. And black holes are the debugging process, or they're not bugs at all, they're features. A designed part of a system we barely comprehend. And if they're features, the tiers they create might not be accidents. They might be messages. In the next chapter, we follow that trail. Because in one repeating gravitational pattern, buried deep in Lagu's raw data, scientists have found something that doesn't behave like noise, or gravity, or chaos. It behaves like a signal, and it might not be from here. Not all mysteries scream. Some whisper over and over again, until the repetition becomes impossible to ignore. In early 2025, an independent team of researchers analyzing archived LIGO gravitational wave data found something strange. Amid the violent spikes and chirps of black hole mergers, there was a pattern. A faint but persistent beta-gravitational signature that repeated every 23.1 seconds, identical in shape and amplitude across 3 separate merger events. It wasn't noise. It wasn't an instrument glitch. It was a pulse. And that pulse didn't match any known astrophysical source. Not neutron star quakes. Not pulsar harmonics. Not seismic contamination. It was a structure in the waveform itself, nested in the post-merger decay, appearing like a drumbeat echoing through a collapsing cathedral. The team, led by Dr. Amina Chowdhury at the University of Cambridge, published the findings cautiously. They called it an unexplained, recurring gravitational phenomenon. But behind closed doors, they were asking another question. What if it's not a phenomenon? What if it's a message? Chowdhury's team passed the waveform to specialists. In signal analysis, people trained to find structure where none should exist. One of them, Dr. Eric Zane, formerly of the Search for Extraterrestrial Intelligence SETI, had spent his career combing radio waves for alien whispers. He immediately saw something different. The waveform, when mapped using a Fourier transform, showed non-random intervals, a repeating modulation, not chaotic, structured. Zane converted the pattern into an audio file, slowed it down by a factor of 1 billion, and played it. It sounded like clicks, mechanical, deliberate, rhythmic. He ran it through SETI's pattern matching algorithms. The AI flagged it. Possible non-natural periodic structure. Confidence, 72%. For SETI, anything above 50% is worth investigating. This wasn't radio. It wasn't light. It was spacetime itself, oscillating with intention. Dr. Chowdhury pushed further. She compiled the spikes from all known occurrences and applied a basic data compression algorithm just to see if the signal contained redundancy. To her astonishment, it did. The waveform could be compressed by nearly 60%, far more than expected. For a random astrophysical event, that level of compression suggests language, information, but from whom? The idea that an alien civilization could encode a message in gravitational waves may sound absurd till you remember that gravity travels undisturbed across the cosmos, unaffected by gas, dust, or radiation. Unlike light or sound, it doesn't scatter. It's the most reliable long-range carrier in the universe. If a sufficiently advanced species wanted to leave a message note for someone across the stars, but across time, gravity would be the way to do it, and where better to plant that message than in a black hole merger, the loudest, most detectable gravitational event in the known universe. But here's the twist. What if it's not aliens? What if it's the universe itself? The idea sounds impossible, yet quantum cosmology leaves the door open for something far stranger than intelligence, self-reference. The universe as a computational system might not just evolve, it might communicate, a form of feedback loop, broadcasting entropy, order, or structure through the only medium immune to decay. Spacetime.Kim, the simulation theorist from Chapter 13, believes the 23.1 second pulse could be a heartbeat, a diagnostic signal from a deeper layer of reality, a ping from the substrate that keeps the program running. It's like BIOS for the cosmos, he explains. A basic check to make sure the system is intact. Others disagree. Dr. Chowdhury has begun exploring another theory, one that terrifies her more than the idea of aliens or simulations. She believes the signal could be a warning. Each occurrence of the 23.1 second pulse followed black hole mergers, involving extreme spin rates conditions theorized to be capable of tearing spacetime. The pulses only appear after the collision of the event that might have caused a breach. What if the signal isn't meant to inform? What if it's meant to contain a sort of cosmic quarantine, a fail-safe broadcast, a way of alerting whatever lies beneath, that a tear has occurred like tripwires across the skin of reality? The idea is speculative. No one can prove it. But then came the final twist. In a recent update from LIGO, a new waveform was recorded on ordinary black hole merger in a distant galaxy. But this time, the post-merger signal showed something new. Not one pulse, two, spaced precisely, 23.1 seconds apart, then 3, then 4. It hasn't stopped, as of this recording. The signal is repeating every 23.1 seconds indefinitely. It's the first time such a pattern has persisted, looping with no decay, no end. Dr. Zane, upon hearing it, said nothing for several minutes. Then, in a whisper, "I don't think we found the message. I think we just entered the chat." In the final chapter, we return to the source, the black holes, the anomalies, the signals, and we ask the only question left: if space-time is tearing, what lies on the other side? It begins with silence, not absence, not void, but the deep, humming silence of space-time itself, the silence that existed before stars, before structure, before the first particle ever dared to move. And somewhere in that silence, something cracked now across the black canvas of the cosmos. Something is speaking again. We followed the echoes, the spikes in gravitational waves, the mirrored quasars, the oscillating heartbeats buried in LIGO's data. We've seen simulations break, math fold into impossibility, and physicists stare into the rendered face of a black hole and whisper, "This doesn't belong." But the question remains, what lies beyond the tear? If black holes, especially the rapidly spinning, distorted monsters we call Kerr, black holes are truly tearing at the fabric of space-time, then we're not just watching astrophysics at play. We're witnessing a failure of foundations, geometry, time, law, and when law breaks, anything becomes possible. One hypothesis suggests the other side of the tear is pure quantum chaos, a region unbound by classical rules, where cause doesn't follow effect, and time loops endlessly into itself. A computational glitch in the cosmic machine, a sandbox of failed physics. Another theory proposes baby universes, entire spacetimes budding from the tear, branching off like biological cells, each with its own constants, dimensions, an arrow of time. Lee Smolin's evolutionary cosmology resurfaces here, a Darwinian tree of universes, each born from a black hole in its parent. In this view, black holes are not just ends, they are WOMBs, but there is a darker possibility, that the tears lead not to beginnings, but to escapes. If space-time is a closed system, a stitched-together membrane of dimensions, then a tear could be a release valve, and what leaks out may not be mass or energy, but information, leaking not toward us, but away from us, into where we don't know. And that ignorance is terrifying. In an unpublished interview, Dr. Elena Ruiz returned to the data that started it all, the LIGO spike, the waveform anomaly. After years of research and hundreds of simulations, she came to a conclusion that she refuses to publish, but quietly shares. The signature isn't just gravitational, it's topological. The waveform suggests that something exited. When asked what she means, she hesitates. Then she says the most unnerving sentence of the entire investigation: "Whatever passed through didn't come from here." If she's right, the tear is not just a rupture, but a threshold, a one-way crossing into war from another regime of existence, a place where the constants we hold sacred, like the speed of light or the strength of gravity, are just regional settings. If something can cross over, then maybe it already has. The mirrored quasars, the delayed neutrinos, the repeating pulses, what if these are not effects of a break, but evidence of interaction? Some physicists propose that dark matter, comprising 85% of all mass in the universe yet utterly invisible, could be matter that belongs to a neighboring reality. It's here, but not of here, influencing our universe gravitationally, while remaining undetectable in every other way, a phantom fingerprint of another domain. Others go further. They wonder if consciousness, so poorly understood, so strange in its resistance to reductionism, might not arise within the universe, but at its boundaries, a product of spacetime's tension with something beyond it, a shadow of another mind. Pressing against the tier, we are drifting toward metaphysics. But then again, perhaps physics was never separate. Perhaps every rule we've built is just the operating system of this bubble, and what lies beyond is neither absurd nor supernatural, but simply next. So, what does it mean? It means the universe is unfinished. It means we live not in a closed book, but in an open script, one being written in real time by black holes and collisions and information we have not yet learned to read. And if those gravitational pulses are messages, and those space-time anomalies are scars, then the story being told isn't just about astrophysics. It's about origin, about contact, about whether we are alone, not just in space, but in reality itself. As we pull back from Sagittarius A*, that slow-spinning wound at the center of our galaxy, we're left with a feeling that's hard to name. Not fear, not wonder, something in between, an ancient question reborn. If black holes are tearing at the seams of spacetime, what's waiting on the other side to meet us? If reality is breaking, will we even know it's gone? Black holes may be more than cosmic graves. They could be keys, errors, or messages. Subscribe if you believe the universe is more than just stars and dust. Comment your theory below maybe. You're the one who'll decode what's leaking through the dark.